So
Sure.
our next speaker for today is Thomas Mussmann, and he's gonna talk to us about reconsidering integrating factor, keeping consistency in an introductory ODE curriculum.
All right, thank you so much for the kind introduction, and thank you for being here to listen. Today, what we're going to talk about, once I get my pointer working, is reconsidering integrating factor. So when we started teaching ODEs and differential equations, the goal of kind of my whole talk is to try and create a consistent thread that students understand and teachers can teach throughout the differential equation class. And so that's kind of my focus. And the first real topic we're going to talk about is integrating factor. But before we do that, we are going to we're going to talk about how a traditional course goes. So traditional courses start in first order ODEs. We teach a couple techniques, right? We teach how to classify. This is what an ODE is. This is, of course, we talk about order and linearity and homogeneity and all those kind of things. And we teach two techniques in first order: separation of variables, integrating factor. And then our process kind of looks like we check to see if the ODE, first order ODE we found was linear and if it's homogeneous. And then whatever the technique happens to be correct, we use that technique. And then we transition in second order, we transition to this idea of, well, sometimes we teach reduction of order, sometimes we teach variation parameters, but almost everybody teaches at least auxiliary equation and undetermined coefficients. But there's a major gap here between the process that we use. When we talk about second order, we have to classify homogeneous or non-homogeneous. Then we solve the homogeneous ODE. Usually it's auxiliary equation, although there are other techniques out there that are sometimes taught. And then we kind of go into solving the non-homogeneous using their undetermined coefficients or variation parameters. And then systems takes the same idea, but then we move it into kind of the eigensystem and solving the eigensystem to solve the ODE. And then we can also do undetermined coefficients and variation parameters in the same realm. So there's a lot of, and then the process very closely mirrors second order. So I'm kind of trying to highlight here is this process here. To many of the students we taught, it felt very black boxish, right? Like you hand the technique, your ODE, and out comes an answer, right? And then they move into second order. And now they have to think more. Now they have to think about homogeneous. Is it homogeneous? Is it not? What does the homogeneous part of it look like? And how are we going to combine the solutions? And so the idea is how do we replace integrating? Well, my proposal will be to replace integrating factor to kind of rectify this I won't call it maybe a discontinuity, right? In as much as things like this have discontinuity. So we'll start off talking about a second order equation. All of you hopefully can see pretty quickly. We'll solve the homogeneous equation and we find our homogeneous answer that looks just like this because we find the roots of, m plus 1 and m plus 2 or m, right? That would be the factoring of this homogeneous equations. We do some undetermined coefficients where we guess this as our non-homogeneous solution. We substitute it in the equation, find out that a equals 1. And so that's our non-homogeneous solution. And as we can see, we combine the two or add the two together in order to create our general solution before we apply initial conditions. And on the other side, of course, we can do this in first order, but we don't like to because it's not as powerful. In first order, we have the ability to solve this equation using the auxiliary equation, but the auxiliary equation is limited because it only can work with constant coefficients. And we would rather, integrating factor in the past has had this ability to deal with a function as the coefficient of y instead of just this constant coefficient. Right, so this is how we would consider the general, or I guess this would be in standard form of a non-homogeneous first order linear ODE, right? And what I'm proposing is the first thing we'll do is we'll put it into, or consider the homogeneous equation. So we take f of x, we make it 0, and then very quickly we see that it turns into a separable equation. Right, so there's my little bubble that says every first order linear homogeneous ODE is separable because once we get rid of the homogeneous part and we divide through by y, we now have all our functions of y on this side, all our functions of x on this side, and it very nicely comes through and this becomes the homogeneous solution to this differential equation. Right, and if we think about our integrating factor, right, we can see that this answer, the homogeneous solution, exactly corresponds to this portion of the integrating factor. So the next idea then is that we're going to use variation of parameters to solve for the non-homogeneous part. So as a review with variation of parameters, we know that the non-homogeneous solution is not linearly dependent on the homogeneous solution. And so kind of in general, the way we describe this is we have the non-homogeneous solution is the homogeneous times some non-constant function. In first order, this is how it looks, although most people don't use it in first order. In higher order, this is how it looks, right? So we've got y1, u1, y2, u2, etc., depending on your order. And then in systems, we see these are the column vectors, or they would also be eigenvectors or eigenvectors that become functions. They're a vector function that become each column of this matrix, depending on the order of the system. And then we multiply it by the kind of the non-linearity generating the u function in order to find the answer. And then based on how we assume the solution or assume the non-homogeneous solution, we substitute the non-homogeneous solution in and substitute into the ODE and solve. So just as review, we're going back to the same equation, right? This is a first order in standard form. We already found its solution, its homogeneous solution, or at least the one homogeneous solution. We're missing the C, but when we go to general form, we'll multiply it by C. And then we're assuming that our non-homogeneous solution looks like this from the earlier slide. When we take its derivative, it becomes this using the product rule. And then we substitute it into the ODE, right? So this is y prime right here. This is y right here. And here's p of x and f of x. Then we do some rearranging, and because y1 is a solution to the homogeneous equation, then this term right here becomes 0 and gives us very simply u1 prime of x times y1 is equal to f of x. And we can by substituting u1 in and integrating by both sides, we can find out what u1 of x is. And then on the next side, right, so we've got a review of this is what u1 is, or y1 is, right, the homogeneous solution. And this is u1 that we found earlier on the last slide. And we find our non-homogeneous solution looking like this, right? We combine this non-homogeneous solution that we found, right, with our homogeneous solution. And here's the constant. And it looks exactly like integrating factor, which should surprise no one, right? Like, it's a unique solution to a differential equation. Why should there be two? You should arrive at the same solution. There's only one of them. But the advantage of this technique is it's how we got here, right? So instead of going through the derivation of integrating factor and doing all this stuff, instead of going through the derivation of integrating factor, we kind of force students to go through this, divide into homogeneous and non-homogeneous, and solve each, put them together, then apply initial conditions, which is the same thing we'll ask them to do in second order and make the teaching process smoother. And in terms of lesson costs, there's actually not that much more, because then you just take your lesson you would normally spend on integrating factor and you just introduce first order variation of parameters instead. And so this is my comparison technique. Of course, I'm biased, right? But we first strike at this idea of it makes teaching higher order ODEs easier because we've already taught the techniques and the process that they should know. It demonstrates the power of variation parameters. So that's one of the things that I got a lot when I taught second order ODEs. You get this, well, we'll teach undetermined coefficients, we teach variation parameters. Well, why do we need variation parameters? Undetermined coefficients is way easier, right? And you can make up an argument like, oh, cosecant and secant and things like that. But the real power of variation parameters is that you can deal with a nonlinear or a non-constant function as a coefficient of your derivatives, right? And that you can really see in this approach, whereas once you get to having to use the auxiliary equation, it's no longer kind of, you can't show that power in the same way. And then last of all, right, students are going to leave the ODE course with, well, we're going to try to leave them with an overarching understanding of how to solve ODEs. And if we solve ODEs the same way in first, second, and systems, or first higher end systems, then when they leave our course, they will leave with this idea of when I have an ODE, I solve the homogeneous, I solve the non-homogeneous to put them together, and it will help them to kind of keep that one idea in their head of how to approach a differential equation. On the other hand, like integrating factor does have its values. Integrating factor is used in some methods to solve systems. Integrating factor is a kind of clever technique that I would like my students to know and be able to emulate. But for us, many of them are kind of looking towards the engineering side and not quite as interested in kind of clever calculus tricks and things like that. And kind of it's show me the formula at the end and I'll work my way through on the test. So that's kind of where we intend to switch here in the next semester. So here's how our curriculum kind of adjusts, right? We remove integrating factor and replace it with variation parameters. And then we kind of have the same technique with maybe this is the same as classification, and then we just solve homogeneous, non-homogeneous, and then put them together and apply initial conditions. So the next thing we want to talk about is how to transition. So I know in both the ZIL textbook I used and in the Voice Suprema textbook that I learned from, we went straight from first order to higher order. And in this, I probably should write higher order instead of second order, but that's where we start is in second order. And the process changes, right? So whether you're transitioning from first order to second order, you start guessing solutions instead of being able to solve explicitly for them in systems. Now we jump into this eigen system ideas and sublinear algebra. And so arguably, my opinion at least, is you're going to have to switch a little bit of the technique idea whenever you go to second order or to systems. But the part that I felt like was significantly easier when you transition to systems is the modeling aspect, right? So we're going to propose that you put systems first and teach it first. And the reason is so this is like a Newton's cooling law, right? We take a cold glass of water, or Gatorade in this case, you put it on a warm room and you do the differential equation. Obviously, eventually gets to the temperature of the surrounding room, right? But we can easily make that a second order differential equation when we put it in a cooler, right? The cold water in the cooler warms up the cooler warms up the air, or I guess vice versa, right? But it very quickly turns into a second order differential equation. Or not second order, it very quickly turns into a system, right? Because the boundary between the cooler and the water is the input for the next system. Right, and we can do the same thing in a mixing tank, right? We teach them this is how to set up a mixing tank. Now you can put two of them together, right? We set up radioactive decay, and you can do either chain radioactive decay or some kind of diffusion inside a nuclear reactor. And that's kind of where I like the idea of switching, at least especially if you're doing a modeling first, of switching first to systems before you go to second order, and especially in terms of physical phenomenon, right? So whenever you're teaching modeling, you're always going, well, here's Hooke's law, well, that's springs, but right, or here's Newton's law of cooling, or here's I forget whose law it is for how fast a tank drains, right? That has an open hole, but it's also a differential equation, right? But you're taking these physical phenomenon that you have laws, and you're basically teaching a physics class and saying, here are the laws you should use and apply. And in this case, the nice part is when you transition to systems, you don't have to reteach those laws. You don't have to jump into kind of force equals mass times acceleration and that type of physics idea. So the next thing I want to point out, though, is if we teach systems first, we don't necessarily need higher order. And the reason for that is we have our traditional spring system, right? Mass times acceleration plus this dampening times velocity plus Hooke's constant times position equals some forcing function, right? That is our differential equation for a spring. But if we know how to solve systems, and if we've taught systems first, then instead of teaching a new method, right, instead of teaching them about the auxiliary equation and undetermined coefficients kind of under a new light, instead we can kind of transform the problem to fit into their framework. So if we, as most of us know, right, you take this x prime equals velocity, and then velocity prime equals, you just simply solve the ODE here, or rearrange the ODE here, and it gives you a matrix or system form of a differential equation. So it's non-homogeneous, but I guess it easily, or it can be solved using the same techniques and gives you the same answer. And if you really only care about position, which is what we do when we teach second order, well, you can just look at the x, and the velocity is just extra information. Right, and so this characteristic equation looks exactly like the auxiliary equation we would expect from it. And then we can do the same analysis that we normally do with characteristic equations and spring systems in using using this systems idea. So for instance, right, we like to talk about critical damping when we talk about springs or things like that, right? And that's when the roots of the auxiliary equation are repeated. But we just tell the students, well, no, it's the root when the roots of the characteristic equation are repeated. It's the same thing, right? So we can approach it in the same way. And here we do the quadratic formula. We find when the discriminant is equal to 0, and that gives us critical damping. Right, and then this one, okay, this is a little bit of a stretch because I love resonance, right? And one usually solves resonance using undetermined coefficients because it's easier, right? So we start off, well, but I'm going to do it in variation of parameters because I introduced variation of parameters in earlier, and it's just so much more beautiful. It's so much easier to show variation of parameters in a system setting than it is to show it in a higher order ODE setting. Right, so just to kind of show that, we're going to go through the resonance example. Yes, you can absolutely do this using undetermined coefficients and it goes faster and smoother, but I love the variation of parameters because it's so much prettier of a proof or so much prettier of an explanation of how we get there. Right, so in resonance, we have this natural frequency, square root of k over m. Actually, this right here should be a 0 as my initial condition, but it doesn't really matter. But here's our differential equation. We got rid of our damping, and that gives us a very nice solution. Right? So this would be our characteristic equation, which tells us that lambda equals plus minus I omega, and then our corresponding eigenvector. And then this makes our two linearly independent solutions that are the solutions to the homogeneous solutions to the differential equations. Right, so we're going to, sorry, I should have put a little more like a line here, right? But this side right here is a review of the differential equation that we have. And this over here is the homogeneous solution that we have. And we're going to take those two homogeneous solutions and we're going to put them together in this script X matrix. And then we're going to take our U function over here that we described earlier, and we're going to multiply X times U to make our non-homogeneous solution. So X times U, and then we take its derivative using the product rule, just like last time. And this is the beauty of what happens, right? So we take this derivative of the non-homogeneous, that's right here. This is A, or the coefficient matrix, times the homogeneous solution times U. And then this is our forcing function, right? And once we cancel out, right, so we know that this X, the script X matrix is the homogeneous solution. And once we cancel that out, because X prime is equal to A times X, that gives us the solution U prime is equal to X inverse times the forcing function, right? So instead of having to force anything through some very tricky analysis to solve for the non-homogeneous solution, in this case, we just, I don't want to say just, because just is a pretty hard word when you're inverting a matrix of functions, but this is a 2x2 matrix. You take the determinant, it's going to be cosine squared and sine squared, which is going to be, usually turns out pretty easy. Sometimes there's an e to the negative alpha t in there, but it's not horrible. Then we kind of go through the math real quick, right? We find U is, if this is U prime, then U is the integral. This is the matrix inverse of script X. This is F. We do the matrix multiplication. So this is the matrix multiplication, comes out this way. Then we do the integration. You'll have to trust me that I did it right. But this is the answer that we get out for U. Now we multiply U times that X script matrix, because that was how we defined the non-homogeneous. And so we find the non-homogeneous solution is script X times U, which here is script X again. And then this gives us the exact same solution as if we were using variation of parameters. So our position function, right? So this is the position function here. X gets this increasing amplitude, right? So the amplitude is linearly increasing with time times one function, and then we take its derivative and we get increasing speed, but that's not quite what we're focusing on. More what we're focusing on is this when we're talking about resonance, is this continually increasing amplitude of oscillation in the X. So this is kind of the summary of where or kind of my argument for why we should teach systems first. And I'm not sure quite yet whether I'm pitching systems first or systems only. We haven't, this is kind of stuff we'll be doing next semester when we adjust our course over the summer. So systems first / only, we particularly like the only because it saves time. So if you don't teach higher order differential equations, it gives you extra time in your course to do other things. It's an easier modeling transition from first order. And then for us, variation of parameters is way more intuitive in the higher order or in the systems world rather than the higher order. So for us, what we're going to do next semester is we're going to teach systems first, and then with that variation of parameters. And then when we teach higher order, we'll teach undetermined coefficients, because undetermined coefficients is an easier process in the higher order systems. And then, right, if you're doing both, still transitioning back to higher order ODEs is smoother. And so, I mean, that's always going to be the case. If you teach systems first, higher order is going to be easy. If you teach higher order first, systems is going to be easier. That's kind of the truth of the matter. And then if you do both, I think you take an advantage of undetermined coefficients. It's easier in higher order. And then we also repeat material if we go through both. What do we do with our extra time? Well, the first that we gain, so if we happen to not teach higher order differential equations and just kind of teach the substitution method, our transform them into a system, the advantage we get is we get more time. And I would argue you have to spend some time on linear algebra. If you're going to focus on systems, you have to be teaching matrix inverses, eigensystems. And for us, they're all incoming freshmen. So we have to teach them this linear algebra because we can't assume that they've had it before. Maybe if you're teaching a little further on in an engineering sequence, they might have seen other linear algebra already. And for us also, the extra time can go towards modeling and kind of, especially at an engineering focused school, in terms of pushing students towards this we use math to model phenomenon, especially differential equations. So this is our proposed new curriculum. Right? So we're dropping integrating factor and instead using first order variation of parameters, and then we take systems and slide it over second order. And that's where I would like to be. As I said, next semester we'll actually teach higher order, but this is I think where we would like to be in the long run in a couple of years. So my thanks to my office mates, Kevin Quigley and Devin Silmer. They've both done a lot of discussing with me about this idea and how to implement and present it. And then, of course, much of our basis for what we call normal teaching, which there is no such thing as normal because everyone does it their own way, but it comes from Zill's differential equation textbook and Boyce Trapima's differential equation textbook. I guess those are the ones I've known as standard, but I'm sure other people use other things. So with that, thank you for your time and attention, and I look forward to any of your questions.
Thank you. Any questions for Thomas? Yes, Mike.
First, I'll say I've been doing the first part of your thing for a while. I found it in Heron, Orsett, and Wanner's book on numerical solving of differential equations. They do the first order linear without the integrating factor and in the same way that you do it. And when I saw that, it just seemed so much easier. I teach it as a process, not as that final formula. So
right.
That you solve the homogeneous and figure out what that is, and then plug that back in, and then solve your new differential equation. So, I mean, that's just, I mean, I think that's a time saver. I don't think you don't really lose much other than if they go to another course and somebody tells them to do the linear, talks in terms of the factor, and then the student might be scratching their head a little bit. For second order, I guess I traditionally, whatever, I usually teach, some qualitative aspects of second order equations that, get the concavity from the second derivative and the slope from the first derivative, and you look at the second order equation, and then you end up with theorems like the separation of the roots that they alternate, and and independent solutions. And I mean, I'm not teaching to engineers, so I tend to include some more mathematical type results. I don't know, I suppose you could do that with systems, but I kind of like it being second derivative, first derivative, and the function being part of the equation, I guess.
Right. Well, thank you for the input. Yeah, I guess it's the first time I'd kind of seen it, and the first time one stumbles across things like that, they think that they're new and interesting. And I guess if you've been teaching it for a while and happy with it, hopefully we'll find ourselves that.
Yeah, I think
as
that'll
well.
be easy for you.
Yes, yeah. I guess I mean my thoughts on a higher order would be, I think you can still explore like the second derivative ideas, right? Like the
Mhm.
from the second order equation, but then just when it comes time to solve it, you don't be like, oh, it's time to go to the auxiliary equation. You just say it's time to go to the characteristic equation.
Right,
I mean,
right. You
yeah,
could just put the second order equation to the side of the system, I guess, and say,
right.
I mean, I'm imagining how I might do it. I mean, if I was going to do what I normally do, then I
Right.
guess, it's really just this, and we'll look at the system. And
Right. And there's a lot of higher order modeling and ideas that I think are like important, right? Like I'm not saying, especially on the modeling and analysis side, I'm not trying to just like ignore them, right? Because like acceleration and mass and forces are like part of physics and engineering and all the things that people do with ODEs. So yeah, but just that you can kind of you don't have to teach auxiliary equations, kind of what I'm trying to point out.
Well, it'll be interesting to see your textbook when you get it written.
Thank you. Thank you. Yeah. Well, for the moment, I think we'll just pick chapters in the correct order from ZIL, but we'll see how that works.
Yeah.
But thank you for the comment.
Yeah, that was great, because I never thought, I was kept thinking when my students were just doing a formula method for integrating factor, there's always a trouble they're not understanding in depth. So this is a great way of really rearranging some of the things, and this fits really in depth of the learning. That's great. Thank you so much. And I know the session ended technically at before 2 minutes, but is there any quick questions for Thomas?
So I wanted to say that I found this really fascinating. I actually teach system dynamics and not math, so hearing you kind of integrate that in throughout the whole class would be really fun for me to be able to teach students that have taken ODE with you.
Yes, and you teach on the engineering side, is that right?
Yeah, right. So mechanical.
Yeah. I've spent some time. I think Major Quigley, Kevin alluded to it, but we do a lot of interdisciplinary stuff, and with that, like I myself have to go like make connections to help the students make connections. And so I've been over in our mechanical engineering department a lot, and they all very much, they love I think they call it the phase portrait, where you plot like velocity versus position, or I don't remember what exactly they called it, but something to that extent. And it comes straight out of solving the system rather than coming out of solving, kind of just the higher order half of it.
Mm-hmm.
And this is great stuff. I would say, if I don't know whether you have plans of publishing this in Primus Journal or some journal, how to arrange curriculum on this. This is a great stuff.
All right. Well, thank you.
All right. Any other questions? Oh, sorry. Go ahead.
No, I actually, let's wait and see if there are any other questions, and then I wanted to make a plug for the next session.
All right. Any other questions? All right. Let's thank Thomas for a great talk.